There is a terrifying paradox. The most dangerous place on the moon might also be the place that holds the most valuable resource humanity has ever searched for beyond Earth. Every night, we look up at a world that feels familiar, yet after more than half a century, it still holds on to secrets we have never truly touched. And among them, there is one thing pulling the entire world back to the moon: water. Not in plain sight, but hidden in places where, by every calculation, it should not exist. That alone turns it into a mystery, and possibly the key to unlocking the entire solar system. Where can we find water on the moon? How do we know it's there? And how close have we come to overcoming the moon's greatest dangers to reach it? The journey to uncover the answer to this mystery did not begin today, but has stretched across decades. Driven by relentless efforts from space agencies around the world, all focused on a single goal: to determine once and for all whether the moon truly contains water. But in the early days, even scientists were not certain. In 1976, the Soviet probe Luna 24 landed on the moon's surface, drilled about 6.6 feet into the soil, and returned to Earth with just 170 grams of samples. The analysis results were surprising. Traces of water were found, around 0.1%, and the concentration even increased with depth. But this discovery was quickly questioned because similar small amounts of water had appeared in earlier samples, such as those from Apollo 11, and were all believed to be the result of contamination from Earth. So, instead of resolving the mystery, Luna 24 pushed the question back to square one. Does water on the moon truly exist? Or is it all just a scientific illusion? Nearly 2 decades later, a new clue began to reshape how humanity saw the moon. In 1994, NASA's Clementine mission discovered permanently shadowed regions near the South Pole, craters that had not seen sunlight for billions of years. This was not just a geographical detail, but a critical hint. If there were any place on the moon cold enough to preserve water, it would be within these shadows, where temperatures remain trapped at extremely low levels, cold enough to freeze almost anything indefinitely. The idea of ancient ice deposits buried beneath the floors of these craters quickly ignited excitement across the scientific community. And just a few years later, in 1998, NASA launched Lunar Prospector with a single objective: to search for traces of water in those long-forgotten regions. But even as we came closer than ever, the answer still did not reveal itself. Instead, every piece of data only deepened the mystery, and the curiosity surrounding it grew even stronger. Lunar Prospector quickly delivered a promising signal. From orbit, it detected large concentrations of hydrogen at the moon's poles. Estimates suggested that there could be tens to hundreds of millions of tons of water ice trapped within those dark craters. But the problem was that hydrogen is not direct evidence of water. It can also exist in the form of hydroxyl, a similar compound that is not enough to confirm anything. To settle the question once and for all, scientists made a bold move. In 1999, Lunar Prospector was deliberately guided to crash into the South Polar region, with the hope that the impact would eject material into space, where sunlight could allow telescopes on Earth to analyze it and detect traces of water. But when everything settled, no clear signal emerged. No confirmed evidence, no final answer. Only a mystery that remained unresolved. It wasn't until 2008 that the story truly took a different turn. India launched the Chandrayaan-1 mission, and this time the approach changed completely. Instead of observing from a distance, they carried an impact probe designed to plunge toward the surface, directly scanning the thin layer of space above the craters and searching for traces of water in vapor form during its descent. The idea was simple, but bold. If water vapor existed, it would be detected just before the probe hit the ground. After separating from the main spacecraft, the probe descended toward the moon's south pole in less than half an hour, continuously transmitting data in its final moments. And then, for the first time after decades of doubt, the answer emerged. In the signals it sent back, there were clear traces of water. Not long after, another instrument aboard Chandrayaan-1, operating from orbit, confirmed it once again. Water truly exists on the moon. But for NASA, that still wasn't enough. Indirect signals could not replace undeniable proof, and so they decided to carry out a far more daring experiment. The L-Cross mission was born, flying alongside the Lunar Reconnaissance Orbiter with a single objective: to definitively confirm whether water ice truly exists inside the permanently shadowed craters at the moon's south pole. The design of L-Cross was almost crude, yet remarkably clever. Instead of carrying complex instruments, it made use of the Atlas V rocket stage that had launched it from Earth, keeping it until it approached the moon, then separating it and guiding it straight into a crater buried in darkness. This impact was not the end, but the beginning of the measurement. Unlike previous attempts, L-Cross did not rely on telescopes from afar, but instead flew directly through the plume of material ejected by the collision, analyzing it in real time. This was no longer indirect observation, but the first time humanity truly touched what had been hidden in the moon's darkness. When the impact occurred, a plume of material was thrown up from the crater floor, rising out of the shadow and, for the first time, coming into direct contact with sunlight. In that brief moment, any water ice or volatile compounds instantly vaporized and broke apart into their fundamental components. Exactly what the sensors on El-Karas had been waiting for. The spacecraft flew straight through that plume, collecting data in real time before completing its mission with its own descent to the surface. Behind it, the Lunar Reconnaissance Orbiter continued observing the remaining material for deeper analysis. And this time, the results were no longer ambiguous. The data revealed that inside those dark craters lies an environment far richer than expected, with the presence of hydrogen, ammonia, and methane, components that could one day become fuel. Most importantly, the signals provided compelling evidence that the hydrogen at the poles is not just a chemical trace, but is directly bound within crystals of water ice. A debate that had lasted for decades had finally found a clear answer. Today, estimates suggest that the moon may contain up to hundreds of billions of kilograms of water ice, an enormous figure, almost impossible to truly grasp. But that very fact raises a deeper question. How can water exist in such an extreme environment, especially in the form of ice? wouldn't it be scorched away and lost to space under the intense heat of lunar daytime? In reality, surface temperatures on the moon can exceed 212 degrees Fahrenheit in regions exposed to direct sunlight, more than enough to destroy any trace of water. But the entire story hinges on one key detail: direct. In places where sunlight never reaches, temperatures plunge to extreme lows, cold enough to lock water molecules in a frozen state almost permanently. And this exists because of what seems like a minor detail: the moon's very small axial tilt. It is this feature that creates craters near the poles that never see sunlight for millions, even billions of years. If water was ever delivered here by ancient comets, then these shadowed craters are the perfect place to preserve it, like frozen vaults locked in time, explaining how water can exist in places where it should not be able to exist at all. Lunar Reconnaissance Orbiter has completely reshaped how humanity sees the moon. Before that, its surface was believed to be absolutely dry, and if water existed at all, it could only be trapped in small pockets deep within permanently shadowed regions. But as it scanned across each area, LRO began to detect something no one expected. Traces of water molecules were not confined to the shadows, but appeared directly within the regolith spread across the surface. The moon is not entirely dry. It is only dry in a way we had never fully understood. This extremely small amount of water does not remain still. It moves over the course of a day, almost like a fragile cycle. As temperatures rise during the daytime, the traces of water seem to disappear, only to reappear when the surface cools at night. That suggests an almost unbelievable possibility. Water on the moon is not just being stored, but may be continuously forming or being retained through some unknown mechanism. And so, a new question emerges, replacing everything we once thought we understood. If such a harsh environment can destroy water within hours, then what is creating it, or what is allowing it to survive there at all? To explain this phenomenon, scientists have proposed multiple hypotheses, and none of them are simple. One possibility is that micrometeorites constantly strike the surface, carrying small amounts of water and leaving behind traces. But another mechanism is even more compelling. The solar wind carries hydrogen, which interacts with oxygen-rich soil to form hydroxyl, and subsequent microscopic impacts continue transforming it into water. These molecules do not exist openly, but are trapped within the regolith or hidden between dust grains, just enough to avoid destruction by sunlight. If that is true, then the entire picture changes. Water is not only confined to the shadows at the poles, but may exist in extremely small amounts across much wider regions. And that opens up a critical possibility. Lunar bases may not need to be built in the most dangerous locations, but could instead be established in more accessible areas, where resources that once seemed non-existent may actually still be present. The moon is almost not tilted at all, and that small detail has created places that have never seen sunlight for billions of years. Near the poles, there are craters completely submerged in darkness, where the sun never reaches, no matter the day or night, season or year. And as expected, these places are cold, but no one anticipated just how extreme that cold would be. While the moon's equator can rise above 212 degrees Fahrenheit during the day, and drop below -148 degrees Fahrenheit at night, inside these craters, temperatures plunge to around -418 degrees Fahrenheit, colder than many distant planets in the solar system. This is no longer just a harsh environment, but a permanent thermal trap, where everything can be frozen and preserved almost indefinitely. That is what makes them ideal storage sites, not only for water ice, but for many other volatile compounds trapped for billions of years. But what makes the picture even more intriguing is that water does not exist only in the darkest places. Observations from Sofia show that even in sunlit regions there are still traces of water, although extremely small. At Clavius crater, water was detected at very low concentrations, almost negligible compared to environments on Earth, yet enough to prove something critical. Water on the Moon is not confined to darkness, but may exist, however faintly, across the surface. And that makes the entire story more complex than ever. Water on the Moon is not just a scientific discovery, but a resource that could redefine how humanity approaches space. It is often compared to the oil of the universe, because if it can be efficiently extracted, it could become the foundation for sustaining life and long-term operations beyond Earth. At a basic level, water can be recycled for drinking, daily use, and even to support agriculture in closed environments. But its true value lies in a far more strategic application: rocket fuel. By splitting water into hydrogen and oxygen, the core components of many modern propulsion systems, the Moon could become a refueling station in space. This would address one of the biggest barriers in space exploration: cost. Every kilogram launched from Earth requires an enormous amount of fuel, and the farther we go, the heavier that burden grows exponentially. But with gravity only 1/6 as strong, launching material from the Moon becomes significantly more efficient, even across greater distances. If fuel can be produced directly there, humanity will no longer be bound by the limits of Earth, and venturing deeper into the solar system will no longer be a distant ambition, but a realistic next step. While the question of water has not yet been fully answered, another race has quietly begun. Spacefaring powers are no longer just observing the Moon, they are preparing to claim it. China, along with Russia and its partners, is planning a series of Chang'e program missions, aiming directly for the South Pole with ambitions to establish a robotic station within the next decade. On the other side, the United States is pursuing the Artemis program, gradually working to return humans to the lunar surface after more than half a century of absence. For the first time since 1972, the idea of humans setting foot on the Moon again is no longer distant. It is steadily becoming reality. And when multiple nations set their sights on the same destination, the question is no longer, should we return, but who will get there first? Growing interest has transformed the Moon into a new kind of strategic territory, where every move carries long-term consequences. But what truly drives this race is not just science or prestige, but what lies beneath the surface. One of those things is helium-3, an isotope extremely rare on Earth but potentially far more abundant on the Moon. In theory, it is an ideal fuel for clean nuclear fusion, producing almost no hazardous waste. On Earth, helium-3 exists in concentrations too low to be economically viable, making large-scale extraction nearly impossible. But on the Moon, where there is no protective magnetic field and the surface has been bombarded by the solar wind for billions of years, the conditions are entirely different. And if technology advances far enough to harness this resource, its value could surpass anything humanity has ever extracted before. If humanity wants to avoid relying on tritium, then there is almost only one option left: finding another source of helium-3. And the paradox is that this source may already be right in front of us, on a world that circles Earth every night. Unlike Earth, where a magnetic field shields and deflects particles from the solar wind, the Moon has remained almost completely exposed to that radiation for billions of years. As a result, helium-3 is not swept away, but gradually accumulates within the surface soil. Even though its concentration is extremely low, only a few tens of parts per billion, the crucial difference is that it is not confined to rare pockets, but distributed across the entire surface. That means, if extraction ever takes place, helium-3 would not be the only target, but just one part of a much broader resource ecosystem. It could even be used directly on site, providing energy for systems on the Moon and helping future bases move closer to self-sufficiency. Although there are still many doubts about its feasibility, this ambition is no longer a distant idea. China has openly identified helium-3 as a long-term objective, while other space agencies and even the private sector are beginning to seriously consider the possibility. And if extraction truly becomes reality, it will not happen in isolation, but as part of a larger wave of resource utilization, where everything within the lunar soil could become valuable. But helium-3 is only a very small part of the story. When we look deeper into the lunar soil, a different picture begins to emerge. This is not an empty landscape, but a resource reservoir on a planetary scale. Its surface is rich with metals such as iron, titanium, aluminum, silicon, calcium, and magnesium. Many of them locked within minerals that are difficult to extract, yet once separated, they simultaneously release critically important elements like oxygen and hydrogen. That means simply processing the soil could produce breathable air, fuel for operations, and even water. The essential foundations for any long-term human presence. Even the soil itself is far from useless. It can be transformed into construction material, enabling infrastructure to be built without transporting resources from Earth. And under the right conditions, it may even support basic agriculture. But there is another category of resources, less often discussed, yet carrying far deeper strategic significance. Rare earth elements. On Earth, they are not truly rare, but they are dispersed and extremely difficult to extract, leading to enormous environmental and economic costs. This has concentrated global supply in the hands of a few nations, creating imbalances of power in critical industries such as electronics and energy. And this is where the Moon becomes truly unique. If these elements can be extracted in space, not only would the pressure on Earth be reduced, but the entire balance of global resources could begin to shift. The demand for these materials is rising at an unprecedented pace, especially as the world accelerates the transition to electric vehicles and large-scale energy storage systems. That forces humanity to confront an unavoidable question. Will we keep digging deeper into Earth, or look for another path? Are resource-rich nations willing to trade environmental stability to keep up with demand? Or is there a less destructive alternative waiting beyond our planet? That is when the moon enters the equation as a potential substitute. Even though rare Earth elements there may not be more abundant, extracting them would not carry the same direct environmental consequences as on Earth. If technology advances to a point where efficiency is high enough, space-based mining may not only be feasible but economically reasonable. But the moment resources become the objective, another question immediately follows. Who will control them? Because in the modern world, control over resources also means control over markets. And on the moon, that competition still lacks clearly defined rules. The Outer Space Treaty prohibits claims of sovereignty and militarization, but remains largely silent on resource extraction. That creates a dangerous gap, where everything could be decided by a simple principle. Whoever arrives first gains the advantage. That is why mapping and identifying resource locations, especially water, is no longer just science. It becomes the first move in a race whose outcome could shape the future of space resource utilization and humanity's long-term presence beyond Earth. But extracting water is an entirely different story. And the cold is not even the greatest danger. In the polar regions, where expectations are highest, an almost invisible phenomenon is taking place, and it could kill you before you even realize it. Because the moon has virtually no magnetic field, the solar wind streams directly onto the surface, carrying charged particles into the shadowed interiors of craters. There, the lighter electrons arrive first, accumulating on the surface and creating a charge imbalance with the ions above. The result is the formation of an extremely powerful electric field, reaching levels of hundreds of thousands of volts. This is not a theoretical concept, but a real energy trap, where even the smallest mistake could have fatal consequences. But the danger does not stop there. The entire lunar surface is covered by a fine layer of dust called regolith. And when it becomes charged, it turns intensely electrostatic. These particles do not just cling to everything. They have sharp, glass-like edges, capable of grinding down equipment and infiltrating sealed systems. During the Apollo program, astronauts reported that this dust adhered tightly to their suits and could not be completely removed. It was not just an inconvenience, but a real threat. One that could damage equipment, reduce material lifespan, and even pose health risks if inhaled. On the moon, even the most harmless-looking thing can become a silent killer. Even the suits that once carried humans onto the moon were not as safe as we once believed. During the Apollo program, they were made from woven Teflon, a material that seemed ideal, yet had a tendency to attract and retain charged regolith dust. Combined with an environment already electrified by the solar wind, those very suits could turn astronauts into part of an electrical circuit, similar to the static buildup you get from walking across a carpet and then touching metal. Later experiments even showed that when Teflon is coated with simulated lunar dust, the risk of electrical discharge increases significantly. But what is striking is that during the Apollo missions, this phenomenon rarely caused serious problems. The reason lies in the landing locations. All of them took place in regions constantly exposed to sunlight, where solar radiation triggered the photoelectric effect, helping to balance electrical charges and greatly reducing the buildup of dangerous energy. However, that will no longer hold true if humans move into the permanently shadowed regions near the poles. where sunlight never reaches. And in those places, everything becomes far more dangerous. The challenge is no longer just temperature or dust, but the combination of all three: extreme cold, a hostile environment, and electrical charges that can reach lethal levels. To survive there, next-generation suits will need to do something never required before: not only protect against the environment, but actively dissipate electrical charge, preventing any risk of discharge. But this is a difficult problem. Insulating materials like rubber may sound like a solution, until they are exposed to conditions where temperatures can drop low enough to destroy conventional structures. And that is the limit current technology is still struggling to overcome, as humanity moves closer to turning the most dangerous regions of the moon into places we can reach and survive. To deal with this hazardous dust, the solutions being developed are not only practical, but at times feel almost like science fiction. One of the simpler yet effective approaches is the use of liquid nitrogen, with its ability to attract and trap fine dust particles away from surfaces, helping to reduce contamination inside future bases. But, on a more ambitious level, NASA is testing a technology that can actively repel dust. Electrodynamic dust shields, where precisely controlled electric currents sweep regolith off surfaces, windows, equipment, and even spacesuits. Instead of being cleaned, the surfaces essentially become self-cleaning. And if that is still not enough, another direction is beginning to fundamentally change how humans approach exploration. Human-machine interface technology now makes it possible to control robots remotely using only hand movements, opening the door for humans to avoid direct exposure to dangerous environments. Robotic arms, autonomous vehicles, and even extraction systems could operate outside, while astronauts remain safely inside protected habitats. As these technologies come together, a new vision begins to take shape. Not humans conquering the moon by stepping into danger, but by allowing machines to face the risks on their behalf. The journey to reach water on the moon is not always a series of forward steps. Sometimes it is defined by abrupt stops. Just as everything seemed to be moving in the right direction, an unexpected decision brought those expectations to a halt. NASA announced the cancellation of the VYPER mission, a robot designed to directly explore the moon's south pole and search for subsurface ice in regions humanity has barely touched. This was not a concept on paper, but a fully developed machine, once expected to become the next major breakthrough. Yet, after multiple delays and mounting budget pressure, it was shut down entirely, even facing the possibility of being dismantled for parts. The decision left many scientists stunned, because in the coming years, no other U.S. mission is positioned to replace its role. A chance to gain deeper insight into what lies beneath that frozen surface was lost before it could even begin. And in a field where each step forward can take decades, a decision like this is not just a delay, it has the potential to reshape the entire pace of the race. Exploring the moon has never been easy, and recent numbers make that clearer than ever. 5 out of 9 recent landing attempts have failed. But even when missions succeed, nothing becomes simpler. Because the most critical resource, water, is behaving in ways we still struggle to understand. Spectral measurements continue to confirm its presence, yet when we move closer to the places that should be richest in ice, the answers become uncertain. The permanently shadowed regions at the poles remain the leading candidates, but that very darkness conceals everything. No one can say for sure which craters actually hold ice and which are completely empty. A single mistake in site selection could render an entire base useless. Even Lunar Reconnaissance Orbiter, the spacecraft that has mapped nearly the entire lunar surface, cannot see through that darkness because its LROC was simply not designed for it. Then, a new step forward emerged. On December 16, 2022, after a journey lasting 4.5 months, South Korea's Danuri officially entered lunar orbit, bringing the number of nations that have sent spacecraft to the moon to 7. On board was a unique instrument called ShadowCam, developed in collaboration with NASA, an upgraded version of earlier imaging systems, but far more sensitive to light. For the first time, humanity had a tool capable of seeing into the darkest places on the moon. And yet, instead of delivering definitive answers, what it revealed only made the mystery even deeper. With sensitivity increased by 200 times, ShadowCam has completely transformed how we see these shadowed regions. What was once an undefined black void now appears with astonishing detail. One of the first targets was Shackleton Crater at the South Pole, a site previously imaged by the Lunar Reconnaissance Orbiter. But this time, for the first time, humanity could truly look deep into its interior. And what appeared was not what many had expected. Shackleton was not a shimmering ice reservoir, but looked much like other craters, with a rough floor scattered with rocks and uneven terrain. There were no clear signs of ice. One reasonable explanation is that its size may not be sufficient to maintain the ultra-low temperatures required for stable ice deposits. But that does not make the situation any less strange. Within the images, a long trail can be seen where a boulder rolled down a slope, leaving behind an almost perfectly preserved track, a testament to an environment with no wind, where movement can remain unchanged for millions of years. Yet, the most striking detail does not lie with Shackleton itself, but in the broader picture. ShadowCam has observed multiple craters at both poles, but so far, no images have revealed the distinctive reflective signatures of water ice, whether as glaciers or even thin surface layers. This stands in stark contrast to what Chandrayaan-1 once suggested. And the mystery deepens even further with data from Chandrayaan-3. If Chandrayaan-1 marked the first breakthrough, then Chandrayaan-3 was expected to confirm everything with far greater clarity. The Chandrayaan-3 mission marked a historic milestone. It made India the fourth nation to successfully land on the moon, and the first to reach the South Pole, a region considered the key to future exploration and settlement. The Vikram lander and the Pragyan rover returned critical data, expanding our understanding of the moon's chemical composition and geological history, laying the groundwork for future missions. But what stands out most is not what they found, but what they did not find. And it is that absence that becomes truly thought-provoking. Before launch, ISRO repeatedly emphasized the mission's core objective, the very reason they chose the South Pole over any other location. A mystery that has followed lunar missions for years, growing more complex with every study, and one that must be solved if humanity is to maintain a long-term presence on the moon. that question remains unchanged and more urgent than ever. Where is all the water? Chandrayaan-3 was launched on July 14, 2023, carrying a compact yet ambitious configuration, the Vikram lander, the Pragyan rover, and an orbital module responsible for transporting both across space to the Moon. By August 23rd, Vikram, with Pragyan inside, successfully landed right at the beginning of a lunar day, a choice that was far from random, but essential for survival. Because there, time is not on their side. This was a mission optimized for cost in a remarkable way. The entire program cost about 6.15 billion rupees, equivalent to $75 million, far below the average $4.1 billion per Artemis program launch. But that efficiency also came with clear limitations. When lunar night falls, temperatures can drop to around negative 216 degrees Fahrenheit, far beyond what the systems can withstand. A single day on the Moon lasts about 14 Earth days, and that is the full window in which the mission can operate. Everything has to be completed within that brief time frame, because surviving the night is almost impossible. Right after landing, Vikram deployed its ramp, and Pragyan began its journey across the lunar surface. This 27-kilogram, six-wheeled rover carried two primary instruments: APXS for chemical analysis using radiation, and LIES, which uses lasers to create plasma and read the returning signals. Within just a few days, the first data came back. Aluminum, calcium, iron, chromium, titanium, and oxygen were all confirmed. The detection of sulfur at the pole was particularly significant, hinting at geological history and the possibility of past volcanic activity. But among everything that was found, one thing that should have appeared was completely absent: hydrogen, the key indicator of water. That absence did not answer the original question. It made it even more puzzling. Pragyan continued to move forward, centimeter by centimeter, guided from Earth. With a signal delay of nearly 3 seconds, every command had to be calculated with precision. And even the smallest miscalculation could end the mission. That nearly happened when the rover approached a 13-foot-wide crater that had not been initially detected. A stop command was sent just in time. But even in safety, its speed was only about 0.4 inches per second, a pace so slow it felt almost motionless, where every step forward came at a cost. During its roughly 2-week operation, Pragyan never strayed more than about 328 feet from Vikram. Every movement was slow and carefully calculated, because even the smallest error could end the mission. After the near miss with the first crater, its path had to be adjusted, and not long after Pragyan approached another crater, but this time chose to navigate around it. No images were captured from that area, and no signs of ice were confirmed. Meanwhile, Vikram continued collecting data, measuring surface temperatures and at depths of about 4 inches, analyzing the thin plasma environment, a positive signal for future communications, and even recording a rare moonquake. In its final moments, it performed a remarkable experiment, firing its engines to hop about 16 inches and relocate roughly 12 to 16 inches away. A small test, but one that opens a much larger possibility. that future landers may not only touch down on the moon, but also lift off from it. But all of those efforts still did not deliver what the mission was truly searching for. There were no clear signs of water ice. By September 4th, time had run out. Vikram and Pragyan powered down as the lunar night arrived. There had been hope that they might wake again, but that never happened. The final signal was transmitted, and then everything fell silent. ISRO still considers it a success, and they are not wrong. The data collected has deepened our understanding of the moon's environment and history. But, at the same time, it has left behind a difficult void to explain. Because water, the very thing confirmed from orbit, was nowhere to be found when we moved closer. No ice, no frost, no direct trace. And if what Pragyan measured is accurate, then the question is no longer whether water exists, but where the substance we detected from orbit is actually hiding. Even as the mystery grows more complex, Chandrayaan-3 has unintentionally revealed a crucial clue, not from Pragyan, but from Vikram. Using the CHAS-TE instrument, Vikram measured temperature from the surface down centimeter by centimeter. At the surface, temperatures exceeded 140 degrees Fahrenheit, far too high for water to exist. But just a few centimeters below, the temperature dropped sharply, and at a depth of about 3 inches, it had already fallen to around 14 degrees Fahrenheit. A dramatic shift over an incredibly small distance. This suggests that the lunar soil is almost non-conductive when it comes to heat, and, more importantly, it implies that if water exists, it is not on the surface, but trapped beneath it. That may explain why every direct observation has failed. The water has not disappeared, it is simply hidden. Even with only about 2 weeks of operation, Chandrayaan-3 leaves behind a clear direction for the future. If we want to find water on the moon, we may need to start by digging beneath the surface. After everything, what remains is not a clear answer, but a deeper mystery than ever before, as water on the moon seems to both exist, and evade every direct attempt to find it, as if it is hiding right beneath our feet, waiting to be discovered in an entirely different way. And perhaps that is exactly what makes this journey worthwhile. Because every time we think we understand the universe, it reminds us that there are still things beyond our reach. If you are someone who loves space and documentary about space, the moon, thank you for staying and listening to today's story. If you feel this journey is worth sharing, send this video to someone who shares that same curiosity. Leave a comment and let me know what you think, and don't forget to like and subscribe so you don't miss the next stories. Because this exploration is far from over, and we will meet again.